Hi, and welcome to video 3.1, where we're going to be talking about chemical bonding and chemical nomenclature. So the first thing we need to look at is the periodic table itself. The periodic table is divided up into different regions based on their metallic or non-metallic character. So the majority of the S block, with the exception of hydrogen, which is actually a non-metal under our particular temperature and pressure characteristics here on Earth, behaves as non-metal. All the S block, all the D block, part of the P block, and the F block, entire F block, are all metals. Now, when we look at the upper right of the periodic table, our noble gases, this row here, our valence of 7, are called the halogens. We've got nitrogens row, the 3 down there, oxygens, and we have carbon. These are all nonmetals. Now, obviously, there's not many nonmetals. In this particular list, there are actually only 17 nonmetals. Now, there are some right along the middle, which are called metalloids, and they have characteristics similar to metals or nonmetals. So, right off the bat, we're going to remember upper right-hand corner is where we find our nonmetals, and as we move down and to the left, we move into metalville. So what does it mean to be a metal in the first place? Well, let's talk about what metals are. They're shiny and lustrous. They're malleable and ductile, meaning if you hit them with a hammer, they're going to dent, or you can draw them into wire. They conduct heat and electricity well. That means they hold their electrons fairly loosely. Most of them have high melting points. The metal mercury obviously has a low melting point as an exception. It's a liquid at room temperature. And probably the most important thing to remember is that they have a low attraction to their valence electrons. They hold their electrons very loosely. Now, a couple of the ramifications of that is it has a low ionization energy, meaning it doesn't take much energy to remove an electron from one of their atoms. They don't hold them very tightly. They have a low electron affinity. That definition is very similar, meaning that if I give a metal an electron, it's very easy for me to take that one back away from it, okay? And it's, again, same idea. They just don't hold their electrons very well. They have a low electronegativity. Electronegativity is a measure of an atom's ability to attract electrons during bonding. So these have a low electronegativity. And they have large atomic radii, meaning that they are large atoms. That's another ramification of not holding your electrons tightly. They're free to wander a little bit. So the important thing to remember here is that metals are going to lose their valence electrons. They have a low attraction for electrons. So let's move on to nonmetals. Obviously, everything has to be kind of opposite of that. They're not shiny and lustrous. They're actually dull, kind of bland looking. They're brittle. If you hit them with a hammer, they shatter, they break. They're good insulators rather than conductors of heat and electricity. They have a wide range of melting points. Air, for example, is non-metallic. Well, it obviously has a very, very low melting point. Or we have things like carbon, diamonds. They have a very high melting point, so a wide range. These nonmetals have a strong attraction to their valence electrons. So that ramification is it takes a lot of energy to remove an electron from a nonmetal. If you give an electron to a nonmetal, it's tough to remove that away. Again, they have a large electronegativity, meaning they have a strong attraction for electrons. They have a small atomic radius. Why? Because they hold their electrons very tightly, the atom gets small. So nonmetals like to gain electrons. So if we're thinking about this whole analogy about a home, perhaps you live in a very loving home, and there's a strong attraction between you and your home life. So you like to be there, talking with mom, dad, brother, sister, aunt, uncles. Even other kids from the neighborhood like to come over and join. That's just because it's such a loving place. Now, you do not get to wander away very often because you just don't want to be out there in the world. you like to be close to the house. So this kind of describes, for example, some of the behaviors that we see that nonmetals hold their electrons tightly. It's difficult to remove them. They have a high ionization energy. This neighbor that came over, tough to make him go home because your house is so much more fun to be in than his house. In bonding, that would mean that, well, you probably meet other neighbors because the other kids want to actually come over and hang out as well. Okay? They have a high electronegativity. They attract other people's kids. Now, if you happen to be in a metallic household, so if your household was more metallic in behavior, that would mean that you have a lot of ability to roam free. So, you go off into the neighbors' houses and hang out. You can go out into the forest and no one really seems to care that you're gone. It's easy to remove you from that environment. You have a low ionization energy. This other kid that wanted to come over, he really doesn't want to hang out there anyway, so it's easy for him to leave. He has a low electron affinity to that house. Other couple things that would happen. It has no attraction for electrons, or very low attraction for other kids coming to visit. So when your neighbor comes over and he looks, he says, I really don't want to go over that house, and he runs away. Okay? As a matter of fact, it's probably really nice to send you on vacation sometimes because this wants to lose its electrons. So I'll let you decide if your household is metallic or non-metallic. Hopefully it's non-metallic. But you get the idea between the two ideas. Metallic households, their electrons are pushed away. They're free to roam. The kids occupy a very large area. If it's a non-metallic household, everyone's held tightly. It's very small. So as we mentioned, there is something called electronegativity, which is a measure of the atom's ability to attract electrons. And in this particular discussion, it doesn't make any sense to talk about these noble gases on the far right because they don't bond. They don't need to bond. They have a full outer shell. They have a full valence. So fluorine happens to have the highest of all the electronegativities. Francium has the lowest of all electronegativities. So as we move up and to the right in the periodic table, we increase in our electronegativity. Fluorine has a very high attraction for electrons, and as we move down and to the left, we reduce in our attraction for those electrons during bonding. That's going to become important to understand. So the first thing we're going to talk about is called ionic bonding. And this is the bonding between the metal and a non-metal. So let's take a look at an example of two neighbors. One has a metallic character, the other has a non-metallic character. We said that the metallic character means that it has a very loose grip of its electrons, the kids. Non-metals hold them very tightly, very loving. They want to be home. They want to play parcheesi with mom. They want to wash the car with dad. Now these kids, not so happy at the home environment. They actually want to do what? They're going to go hang out at the neighbor's house, right? So when that happens, we end up losing our kids. We end up losing our electrons. And one of the consequences of losing those electrons is that we become positively charged in that process. The consequence of gaining those electrons is that we become negative in our charge. And as we've discussed, one of the four fundamental forces in the universe says these negative and positive forces are going to attract one another. So the metallic household ends up being attracted to the non-metallic household, and they're stuck together. That results in their ability to attract or lose electrons. That's the whole idea of electronegativity. So back to this slide, an ionic bond is the transfer of electrons from the metal to the non-metal. Results from large differences in electronegativity. So it's a transfer. The kids are leaving one house to go hang out at the other. The electrostatic attraction between those ions, pulling them together, the negative and positive forces, results in a very strong bond. So when we want to talk about writing formulas of ionic compounds, we have to determine the formulas and charges of the cation and anion that are involved in the compound first. We're then going to combine the anions in ratio that results in the formation of a neutral ionic compound. So ionic compounds, like any matter, has no charge. We have the same number of plus charge that we have minus charge present in that compound. The total charge of all those positive cations, and being redundant, of course cations are positive, must equal the total charge of all the negative anions in the compound. Then we show the numbers of each element present in the compound as subscripts in the element symbol. So how do we know what their charges are? Let's take a look at that first. Based on their valence, we know that group 1 has one valence electron, meaning it will like to lose one electron. These guys often, not always, will form +1 ions. The second group, having two valence electrons, will try to lose both those electrons so that it has a full outer shell. This group over here, having two s's and a p electron, will try to lose all three as metals and form +3 ions. Now let's change the subject for a second to our nonmetals in the halogen column. These have 7 valence electrons. They really want to gain one more electron to have a full valence shell. They really like to have that full octet. Oxygen's column need to gain 2 electrons. Nonmetals, they want to gain electrons. They like to form -2 ions. Nitrogen's wants to gain 3 electrons. And here in the middle, we have +3 and -3. Well, these guys can either be +4 or -4 generally, depending on who they're bonding to. Okay? And of course, these guys will not form a charge. We're going to come back and worry about that D block and F block in a little bit. But as a general rule, the metals here form a +1 ion. Metals here form a +2 ion. The metals here form a +3 ion. The nonmetals over here form a -1. This group forms a -2. This is -3. And in the middle, we can be + or -4. So let's take a look at that. So we're going to figure out what is the formula of magnesium fluoride. You'll notice now we have an IDE suffix. Anytime I'm dealing with a nonmetal from the periodic table that is acting as an anion, it ends up with an IDE suffix. So we were just talking about fluoride. We could also have oxygen as an oxide, nitrogen as a nitride, carbon as a carbide, phosphorus would become phosphide, sulfur would become sulfide, chlorine would become chloride, selenium would be selenide, bromine would be bromide, iodine would be iodide, etc., etc. So there's not very many of those. The IDE suffix tells you, hey, I'm a nonmetal now acting as an anion. So then what does it mean when we have magnesium fluoride? Well, I've got magnesium bonded to fluoride. What charges are they going to have? Well, here's my magnesium. It's going to form a +2 ion. Here's my fluoride. It's going to form a -1 ion. So I'm just going to list those right here below so I know what I'm dealing with. Magnesium has a 2+ charge, and I'm going to bond that to this fluoride, which has a -1 charge. So we know magnesium has to lose 2 electrons, but each fluoride can only gain 1. So we need to think about this concept of a least common multiple for charge. I have to have as many positives as I have negatives. So the magnitude of charge here is 2 plus. The magnitude of charge here is -1. So at what point would they become equal? Our least common multiple is 2. Meaning I have to have 2 of the fluorides to cancel out the +2 magnesiums. So the formula would be given as MgF2. Now I have 2 of the -1s and 1 of the +2s representing the formula of magnesium fluoride. One of the things you'll see sometimes is people will take the number that appears here, move it to the subscript here, take the number here, and move it to the other side. Because this is a 1, we don't write the 1 there. We never show that. We can do that. We can switch those around as long as we reduce. Because the end result is we're actually just finding the least common multiple, as we did before, to represent an equal number of positives and negatives. So let's try this example. Sodium nitride. Our sodium atom is here, meaning it's going to form a +1 ion. Our nitrogen is here, so nitride is from nitrogen. It will form a -3 ion. So I'll have Na plus for my sodium, N3- for my nitride. Now, least common multiple between 1 and 3 is 3. So how many sodiums do I need to get a +3 charge? I would need 3 sodiums. How many nitrogens to get a -3 charge? Just 1. So the formula of sodium nitride is Na3N. Our next example will be calcium sulfide. And yes, now I've gotten rid of our little cheater numbers on the periodic table, because I can count. Calcium is here. That would be in the +1, 2 column. Okay, it's +2. Sulfide would be sulfur, and that's in the -2 column. So I've got calcium, I've got my sulfide. Now, what's my least common multiple between 2 and 2? Well, they're going to obviously reach the same charge magnitude at 2, meaning I only need 1 calcium and 1 sulfur. Again, if there's a 1 of each, you just don't show any subscripts. Okay? So now let's take a look at aluminum oxide. Our aluminum is over here, where it would be acting as a +3 ion. Our oxide is here, acting as a -2 ion. So a +3 and a -2 have the least common multiple of 6. So how many aluminums would I need to be at +6? The answer is 2. How many oxides would I need to reach -6? 3. So my formula of aluminum oxide, Al2O3. I have as much positive charge as I have negative charge. So there are other ions called polyatomic ions that are groups of atoms bonded together that behave just like regular monatomic ions in the fact that they have simple charges, a +1 charge, a -1 charge, a -2 charge. So let's take a look at a few of these. There is the NH4 ion called ammonium that has a +1 charge. So it behaves bonding-wise like our lithium or our sodium or our potassium, anything in that +1 charge column. It just is NH4, a nitrogen bond to 4 hydrogens behaving as one particle. There's the acetate, -1. We have a chlorate, ClO3, it's -1. We have an iodate. We have a nitrate, NO3-, a nitrite, NO2-. You'll notice that for the most of these, we are using ates and ites as suffixes. IDE told us it was a single element behaving as that anion. So chloride was just chlorine. Well, then we have things like perchlorate, or just chlorate, or chlorite. So all these different names, we have to be very specific about our spelling because there's a big difference between chloride, chlorate, and chlorite. We also have some -2 ions. We have a few -3 ions present. And so this list will be helpful when we start talking about bonding with polyatomic ions, but the rules are going to be the same. So let's take a look at this example. Potassium carbonate. We know that over here is our potassium. It has a +1 charge, but carbonate had an ATE ending, which tells us we're not talking about carbon. That would be carbide. We're talking about carbonate. So now we go to our little list here and hunt around for it. And down here, I see carbonate is CO3, and it has a -2 charge. So there are my 2 ions. The potassium with a +1 charge, the CO3, the carbonate, with a -2 charge. Now all I'm really paying attention to again is the charges at this point. Potassium is +1, carbonate is -2. Their least common multiple here is 2, which means I would need 2 of the potassiums to reach +2, and only 1 of the carbonates to be at -2. So potassium carbonate, K2CO3. So how about ammonium selenide? Well, obviously ammonium is not one of the elements from our non-metal or metal list. So what we're going to do is look at our table, and at the very top, the only cation that's a polyatomic ion we'll be dealing with is NH4+, the ammonium ion. In terms of selenide, selenide is the element selenium acting as an anion, which would have a -2 charge. So there are the ions for ammonium selenide. Now again, we're just going to look at the charges. Ammonium is +1, but selenide is -2. Their least common multiple is 2, so I need to show 2 ammoniums and 1 selenide. But how do I do that? That's a little tricky. There's 1 ammonium. I only need to show 1 sulfur. So how do I show 2 of these? Well, the trick is I've got to show it as a group because I'm trying to show 2 of those ammoniums for every 1 selenide. So NH4 in parentheses with a 2 outside, and then S would give me the formula of ammonium selenide. 2 ammoniums, 1 selenium. So let's take a look at magnesium chlorate. Here is our magnesium, +2 charge position. And the chlorate, not to be confused with chloride, IDE, which would be on the periodic table. Chlorate, not chloride, chlorate is ClO3 with a -1 charge. So there are ions. Magnesium is +2, chlorate is only -1, so I need 2 of the chlorates for every 1 magnesium. And again, because I'm trying to show 2 of those chlorates, I'm going to use my parentheses. Now I've got 2 of the chlorates and 1 magnesium. So one of the things we should probably point out at this point, things we can be very sure of. The elements in this box are always going to represent +1 ions or +2 ions, depending on position. There's a few other important things we should mark on our periodic table. Silver will always form a +1 ion. So if you can actually write it in that box, it's helpful. Silver as an ion will always be +1. Both zinc and cadmium will always form +2 ions as a charge. So zinc and cadmium are +2. And aluminum will always form a +3 ion, as we kind of predicted. So on your periodic table, it's very helpful to have all these things boxed off so that you know if it's something in that column, it's always going to be +1. If it's something in this column, it's always +2. Silver is always +1. Zinc and cadmium are always +2. Aluminum is always +3. Go ahead and write those little charges inside your periodic table. Now, why I'm pointing that out is I've left a heap of metals in this region, a few over here, and on my F block, that I don't know their charge until I see them bonded. The reason is because they can bond to several different things in different ways. So for example, iron can actually form a +2 ion. Iron can also form a +3 ion. So I can't just say iron 3 oxide because they would have 2 different formulas, depending on whether the iron is acting as a +2 or +3 ion. So for all those elements that aren't inside the boxes we put on earlier, we have to use Roman numerals to show the charge. So I can talk about iron 2. Well, what I'm telling you is iron has a +2 charge here. I could also talk about iron 3. Well, iron 3 is simply iron acting with a 3+ charge. Now, that should free it up to make it very easy, because if I'm talking about gold 1, you know the charge of that particular gold is +1. If I say tin 4 IV, you know that tin is acting as a +4 ion. So it's actually really helpful to have these Roman numeral systems, what we call the stock system, to identify what the charge is of those elements that have more than one stable, what we call oxidation state. So let's take a look at a couple examples of that really quick. So here is chromium 3 hydroxide. Looking at the periodic table, I can figure out that the formula of chromium 3 is Cr 3+. That's what the Roman numeral is telling me is it has a +3 charge. Then I can hop over to my polyatomic ion sheet and find that, oh, hydroxide is OH with a -1 charge. So when I combine them, I look for least common multiple. I've got a +3 and a -1, which means they both need to reach a charge of 3 magnitude. So 1 chromium and 3 hydroxides. That's chromium 3 hydroxide. Beautiful. How about titanium 4 bromide? The symbol of titanium is Ti, and of course, because it has a Roman numeral 4, I know its charge is 4+. Bromide, looking at the right of the periodic table, tells me it has a -1 charge. So if titanium is +4 and bromide is -1, I would need 1 titanium and 4 bromines. Titanium 4 bromide. So as we come back to the periodic table, let's review what we just learned. If it is an element that appears in one of the green boxes, it does not need a Roman numeral. I never say magnesium 2 chloride. I just say magnesium chloride because magnesium is always +2. I don't say zinc 2 nitrate. I just say zinc nitrate because zinc is always +2. There's no point in saying aluminum 3 fluoride because aluminum is always +3. That means all of these other metals in this region, in this region, in this region, in this region, and of course our F block, these guys are all going to need a Roman numeral in their name. So I can't just talk about cobalt chloride. I would have to say which cobalt I'm talking about. I could do that by figuring out who it's bonded to. Hey, this cobalt's bonded to 2 chlorides. What charge must cobalt have? Oh, it must be 2. So this is cobalt 2 chloride. Now what do you suppose I would have if I just had COCl? Now it becomes cobalt 1 chloride. Point being, because it's not in one of the green boxes, it needs a Roman numeral in its name. I can't just say tungsten carbonate. I would have to indicate the charge of that tungsten with a Roman numeral. Green box, no Roman numeral. Outside the green box, yes, you need a Roman numeral. And that about sums it up for ionic bonding in terms of taking the name and getting the formula. We'll work backwards a little bit in class, but that really wraps up our lecture for 3.1. Thank you very much.